Okay, so today we're going to be talking about driving characteristics and the limitations that drivers have. And a lot of times, drivers are limited by what they can see. None of our eyes are perfect. And so, to illustrate some of these points, I'll be going through a couple of demonstrations. The first demonstration that I want to share with you has to deal with our field of vision. So, what I want to do is I want you to take a look at this blue dot that you see here. And I want you to keep your eyes on that blue dot. And now I'm going to introduce um, some letters and numbers here. Now, again, keep your eyes on the blue dot. I don't want you to move your eyes off that blue dot, but I will be moving these letters just to show you what I'm talking about. So here, that's the blue dot. If I were to move this over here, you could probably still make out what the words and letters say. But if I were to move it over some more and you still focus on that blue dot, the letters and numbers aren't really as clear as they used to be. And if I were to move it out again, and if you're still just only focused on that blue dot, you may not even be able to make out what those words say. And then, of course, if I move it out some more to the point where it's almost gone, you may be able to see something, but you're not even exactly sure what that is. And so you see, the further we move away, the worse our field of vision gets. And that's the exact same thing that happens when we're talking about a driver driving on the road. You see, his field of vision is pretty good, provided that it's right in line with his eyesight. But if it moves over to the left or to the right, it gets a little bit worse. Similarly, if it goes up and moves down, it's the same type of decreasing field of vision. So we see here that our field of vision is really in a conical fashion. And it really depends on how close we are to the same sight line that the driver's eye is in. And it not only works in that direction, but it also works in this direction, where your field of vision is perfect if it's right in line with the eyesight of the driver. But it gets to be a little bit worse as it moves to the left or the right, and also up or down. So it's conical in this way and in this way. What that all boils down to is something called acuity. And so acuity is the ability to see fine detail. So anywhere from 3 to 5 degrees is clear vision, then 5 to 12 degrees fairly clear vision. Like when I kept that dot there and moved the words and letters over and numbers over. And then beyond 12 degrees is blurred. You know there's something there, but you can hardly make out what that means. And as I said before, everything works in a conical type of fashion. What we call peripheral vision is anything that is outside of the area, so outside of that 12 degrees, but no more than 180 degrees. So we just have a sense that there's something there. And we always have to take into consideration the color blindness, because people may be colorblind, and therefore large contrast in colors are detectable. But if there's not a huge contrast, such as maybe a red and yellow, then it will be very hard for someone to see. For instance, this right here is a picture, or it's some type of ball, but it's a little miniature of the globe. And someone who's colorblind might not be able to see the difference between the blue and the green. But because there is some sort of a contrast, they know that there's a different color there. Which is one of the reasons why people who are colorblind are able to determine the difference between, say, a traffic signal that has 3 lights. Now we know that the traffic signal's 3 lights are ordered. Most of the time you have your red at the top and your green at the bottom. So they'll be able to determine if this is lit, then it probably means go. If this is lit, it probably means stop. But being able to determine the difference in colors may be a little bit hard for someone who's colorblind. So order is important too when we're doing anything with the road. Glare is something else we should be able to consider. especially when we're talking about working in work zones or driving through work zones where um, the night vision is not as great, and therefore the people who are working have to place lights into the field of vision. For instance, I have this light that I'm shining right now, but what if you can consider you driving into the paper and now this light is shining towards you? That glare kind of takes a little bit off of your ability to see and therefore should be minimized. Another thing that we have to consider is something called depth perception. Sometimes it's very hard to estimate how fast vehicles are traveling, and so in some cases, like in this picture shown, we put little markers there to help people who may be traveling, let's just say from an intersection um, that is at this location, so that they'll be able to use the markers to estimate how fast vehicles are traveling. And so depth perception can affect our ability as well. Okay, let's move on to vehicle characteristics. Now, we already know how we're limited as far as our vision is concerned, in some of the ways, but our vehicles are limited as well. Here's a typical vehicle as far as dimensions are concerned. Of course, our vehicles don't look that old anymore, but the dimensions are pretty much the same unless you're talking about like a really, really smart car. Um, where the dimensions will be cut in half almost as far as length is concerned. But the radius, right? The radius is something that is important, and you'll see the difference in the radius between a passenger car, which you can see here that it has a minimum turning radius equal to about 24 feet. And when I show you the truck, you'll see how much of a difference it is. But first, let's talk about the assumptions that we have about vehicles, or like passenger cars. In all of our calculations, we assume, or in most of our calculations, we assume that the deceleration rate, right, so that is the rate at which the vehicles slow down after they start braking, is 11.2 feet per second squared. And then we have the another assumption, which is the driver's eye height. Right? So the driver's eye height from here to about here. All right, we're assuming that that's about 3.5 feet, all right, from the pavement. And all of those come into play because when we're designing with the vision in mind. So we need to know what that line of sight is so that we can design properly and safely. Now again, I wanted to contrast what you saw there as far as the turning radius with the turning radius of a truck. So I don't know if you can see this, but I'll just go ahead and point it out here. The minimum turning radius was 45 for a truck of this size, which is about 73.5 feet in length, compared to a passenger car, which we said was about 20 or 19 feet in length. And so the turning radius here is a lot larger than 27 feet. It's 45 feet. So therefore, if we're designing for a truck, you got to keep that turning radius in mind, especially if it's at a median or something. Here's another uh, assumption that we make, or something that we have to consider. Trucks accelerate and decelerate differently, and we have to account for that when we're designing for stopping sight distances that we'll talk about later. Another thing we have to consider is the acronym PIER. P-I-E-R. All right, and that's the acronym for perception, identification, emotion, and reaction. The time it takes for all of these things to happen is really, really fast. For instance, let's say you're driving along the road and you're driving into the screen here, and then boom, you see that happens. So if this is your first time ever watching this video, then when I did this, you probably had some type of reaction to it. I don't know, you might have moved, you might have jumped, I don't know, but doing this out of nowhere would have caused a reaction. And so the amount of time it takes for that to happen, for you to perceive, identify, have an emotion to it, and then react is about what you think? 1 second? Less than 1 second? Greater than 1 second? Well, if you're paying attention, if you are alert, the time for peer to occur is equal to 0.5 seconds. 0.5 seconds. Now, I know a lot of you, even though you would never admit it, you all are texters. So you'll be driving in your vehicle, probably wouldn't have a phone as old as this, but you would be driving and maybe doing something like this because you move your thumbs very fast and whatnot. But and you would think that you're able to do these things relatively quickly without any harm done. But all it takes is 1 second, and I'll show you. All it takes is a 1 second difference for that action to become something that is either fatal or very severe. And I'll prove it to you by going through a peer equation and example. So the perception reaction time is equal to the following. It is 1.47 times u, which is the speed, times the reaction time. Again, that is the speed in miles per hour, and this is reaction time in seconds. You might be wondering, how do you get miles per hour in seconds to end up as a perception reaction time that's also in seconds? And the answer is that 1.47. 1.47 is simply 5 to 80 divided by 3600. That's what 1.47 is. And if you notice that there are 5,280 feet in the mile, and there's 3,600 seconds in the hour, and therefore we're able to convert this into seconds, and we end up with seconds. And so that's the peer, or the perception reaction time, is done by that equation. So here's the big question. If you know that an alert driver, an alert person, can have a perception reaction of 0.5 seconds, what do you think we designed for? The answer is we designed for 2.5 seconds. Now, that is somewhat of a factor of safety, because sometimes we understand that we're not always going to be having the ideal situation where a person is always going to be alert or knows what's coming up. Okay, so what is the difference between an alert driver traveling 35 miles per hour and a driver that has a perception reaction time of 1.5 seconds? That's what we are going to determine using the equations that we've already learned about. So the first thing I need to do is just go ahead and understand that if I'm talking about perception reaction time, this is the equation that I'm going to use. And I'll just go ahead and place two of those equations out there. So the first one is a perception reaction time 0.5 seconds. The second one here is a perception reaction time of 1.5 seconds. Hey, that might be the difference between someone that's texting and someone that's not. We'll see. Someone who has a perception reaction time of 0.5 seconds, the distance that they will travel is equal to 1.47 times 35 times the 0.5 seconds, which ends out being very close to about 26 feet. Now the other person here may be distracted, playing with the radio, I don't know, but 1.5 seconds is the reaction time, and that equates to about 77 feet there. So that is a difference of approximately 50 feet. Let's go with it. Okay. That is also about 2.5 cars, passenger cars, and it also equates to about a 200% increase. And so just by being distracted by 1 extra second, and you don't have enough car lengths between you, at least 2.5 cars, and you're traveling 35 miles per hour, you will end up hitting someone before you even touch a brake. And speaking on that, the next thing we're going to be caring about and moving towards is the B, which is also called the braking distance. But before moving on to any more on the braking distance, I want to clear up a few things and make sure we're on the same page. When we're designing for any distances, whether it be perception reaction distance, braking distance, or stopping sight distance, which we'll talk about later, we want to do that in multiples of 5. We like nice round numbers in multiples of 5. So if you got a 122, you calculated that, you should go ahead and just round it up to 125. Second thing is, posted speed limits. They're usually posted at 5 to 10 miles per hour over the design speed. So if you design for something for 70 miles per hour, it could very well be posted at either 60 or 65 miles per hour, as far as the law is concerned. The next thing I want to talk to you about is the distances while reacting. They're governed by a couple of things, and we already seen them, but just to put it out there: speed and reaction time. And that reaction time is huge. Sometimes that changes if we know that a driver is approaching a situation that is not complex, therefore they're familiar to it. So that reaction time would decrease, therefore decreasing the reaction distance. And therefore, using that equation would be the same, but the outcome would be different. All right, now here's an example. Again, I think you have the hang of it by now, but if you have a person driving 60 miles per hour, then we want to do some type of design based off of that 60 miles per hour, and that means this is what we'll be designing for as far as the reaction distance is concerned. Now, this is just a reaction, the time it takes to react. We haven't touched the pedal yet. In order for us to figure out how long it takes for them to brake, we have to apply another equation, which is coming up pretty soon. But I just wanted to show you the factors that affect perception, identification, emotion, and reaction. All of these affect it. And you can call liquid inhibitors alcohol, or you can also have any type of drugs. Anything that inhibits you, including fatigue, can also react the same way as drugs and alcohol can. So that's enough on that. Now let's talk about the braking distance. So the braking distance equation is this one right here, and it was all derived from the forces that we see acting on this car and coming from this car that is traveling on the incline. And so you have all the different types of forces. We took the sum of the forces in the X and Y direction, and then we solved for the amount of force, or the amount of force that it would take for a vehicle to brake, and we ended up with that final equation. Now, no one loves to watch videos on derivations, so you just have to take my word for it. And what I also want to show you is that in the end, our stopping sight what we call stopping sight distance is equal to the distance it takes for us to react plus the distance it takes for us to brake, where that is your speed squared. 30 is a factor that stays in there, came from the derivation. This is your friction factor. And this plus or minus is the grade. Meaning if you're on an incline, if you're going uphill, it'll be a plus. If you're going downhill, it'll be a minus. And that grade will either make this number larger or smaller